So this is part 2 of the normalization theory, and we may have many part of normalization theory in the process of lecturing. Today I intend I will probably do just 2 parts. So we'll finish out this part and call this a day. So let's go ahead and look at what we have in module 2B here. Not 2B, but 2B, A, B, C, B, D, B here to learn normalization theory. So chapter 3, after introducing all these important terminology, what we are trying to do and read about is to understand the basic theory behind the normalization theory. This including the understanding of the concept called functional dependency. Functional dependency is described actually by the name, and people like to use functional dependency because in the computer world, you know that in most of the earlier time, the majority of the job a programmer is doing is try to write a function. So you write a function, say write a function to calculate salary. So the function will take all these individual salary and add them up together to an average or something. So those are the functions that you are trying to write into algorithm. And so a lot of time we just using the functional terminology to describe. Functional dependency is actually referring to something happen and output to the other thing, right? So usually a function that we know, and I'll try to write a little bit here by annotate the things on the screen here, right? So when we say function here, a function is usually writing something like this. You probably learned this in your high school. Why? Actually, you know what? I write it incorrectly. I'll use a little bit of time here to make sure I write a thing. Say, for example, this will be a function. Oh, I cannot. I'm still not very good at using the tool here. So this is, say for example, x plus 2. Right, so we have a function here. And functional dependency is basically referring to that your function here, in this case f function here, depends on the input of x. So whatever x change, f change. So f depends on x. So that's basically what function dependency is. So in the database, we are talking about one column and its relationship with another. So in the function, we say one variable in the relationship with another output, right? Variable and output. And here is one column to another. So if one column, you know the value of one column, you can calculate or you can derive the value for another column, then that's called a functional dependency. So that's a basic definition of functional dependency. And we, most of the time as a student, learn this concept by looking at an example. And a lot of these examples seem to be very simple, but sometimes it's misleading. So let's take a look at this example on the slide. It says student ID, and the way we read it is called student ID determine. So the red arrowhead is determine, is a verb. The operator is a determined verb. So student ID determines student name. Using the regular language, we're saying is that once you know the student ID, you know the student name, right? This kind of a relationship is not reversible, and so this is why that a lot of logical deduction theory is becoming useful here, because all these are logical deduction process. Because a lot of time we thought that something is reversible, but they are not, right? Say for example, in this case, we said if you know student's name, do you know the student ID? And in our classroom, for example, we can say, Imran, I know your name. I can look up for your student record, and I know your student ID, right? So using common sense, it seems like, well, there's nothing wrong with knowing the student name and knowing student ID, right? But in reality, there is. So what if there are more than one Imran in my class or in university? Then if I go search for Imran, I may find 2 or 3 or 4, and there are 4 student ID in the student database. If that is the case, then the reverse direction is not true, because once you know student name, there are multiple student ID you can match to. So you don't know exactly which ID belongs to that student name. So that creates the problem of so-called functional dependency problem. So in this case, that we have single direction functional dependency, and this again, every time we try to evaluate the dependency, you have to think about it using a few examples to verify it. Otherwise, it's very confusing. If it depends on your common sense, you say, oh yeah, I know student ID, then become a determinant, and every time you see student ID, it may not be true, right? A lot of times student ID cannot just get what you really wanted for student information, right? So that's what I think should be sufficient reason or example here. So once you know the left-hand side, you know the right-hand side. But once you know the right-hand side, you don't know the left-hand side. The other way of explaining the functional dependency is using the real mathematical equation or real function we just talked about. So everything you can put them into mathematical calculation, and this happens a lot when we are trying to build a report, database report. Say for example, we are looking at you go to Walmart, you buy 5 pizza roll, 5 bag of pizza roll. Each bag of pizza roll is like $10. So you know that using a human computer, you immediately put that at $50, right? But in the computer record, if you think about it, there are some actually issues we can discuss. You can say, okay, I go there and buy pizza roll. That's one piece of information you can keep track in database. And the other piece of information you can keep track is that each pizza roll is $5. So once you have these two information, do you know how much money you spend on your purchase? The answer is obvious, yes. You simply use 5 times 10, right? 5 pizza roll times 10 package. $10 a package, so it's $50. So in database design, earlier time is this become an issue. It's no longer an issue today because again, the issue is memory is so cheap, you don't need to remember that. So you can keep track of the 3 pieces of information we just mentioned: the quantity you purchase, the unit price you purchase, and the total price you spend. So there are 3 pieces of information, right? And you can create 3 columns if you try to imagine creating a database. That is not a problem. But rolling back all the time when the database was expensive, this is actually a problem. There are actually 2 problems. The 2 problems are the problem we talk about why we need normalization theory. Problem number 1, in the slide you see here, extended price. This is called the calculated information or derived information. Calculated information is redundant. Does that make sense? You know the unit price, you know how many units you purchase. You can always calculate the total price. So when you put an extra $50 in there, you're wasting the valuable memory space. So that's called a waste of space. It's not efficient, right? So we want to make sure that the memory is efficiently used. You cannot record that extended price. So that violates the first rules of database normalization. So we don't want to keep track of extended price. Problem number 2 is also the same problem we talked about, data quality. So how can this become a data quality problem? It is because the more data entry you have, the more likely you make mistake. So if you create a database, you have to enter quantity, unit price, and extended price. What if some people has a very bad math training? He put 5 in quantity and 10 in unit price and put 60 in extended price. That's bad, right? That creates potential data entry error. Data entry error is a data quality problem. So a recommendation in this kind of situation in normalization is we're not going to be using extended price, and the extended price can be calculated. But conceptually, the dependency is unit price and unit quantity purchase derive extended price, not the other way around. So you know the extended price, you don't know the unit price or quantity, but so the left-hand side information are more important than the right-hand side. So this is some possible thing. And this particular slide example also give you one good example of something what we call composite key. And so in this case, you have two variable or two column. In database we call them column. Two column determine another column, and this two is called a composite. Composite is another terminology we need to learn and can be confused about in the process. Now this example is very good for class discussion, and I found that usually when we have this remote session, and it's not that good but I'll explain using as best as I can, because in the class session I can question you and trick you, and when you make mistake I can correct you, that you can learn. But in here what I intend to show you is that try to figure out the dependency relationship not by your concept but by your observation, by the fact, not by your concept, right? So this table, obviously we didn't tell you what kind of table it is. You don't know what data you are trying to keep track of, but we're telling you that we have object, color, weight, and shape as three column or three attribute, three column that we are using. And I ask you, which column determine the other column. And so you start thinking about, if I know something by color, do I know the shape of the weight of the stuff? So you start to match this to your real world experience. Say, okay, yeah, I saw that there is a what is that? A mug, a coffee mug, in front of me. Well, it looks like most of the coffee mugs are white, and most of the coffee car has the cylindrical shape in there. So you say, oh yeah, right, I know the column, white color seem to determine the cylindrical shape. Is that true? Yeah, you can immediately tell me that it's not true. I know the color, this white color. It may be the mug. It may be something else. Maybe my tissue box here. Right? Can I show tissue box? Maybe my other stuff here. Right? It can all happen. So the color does not determine the shape or the weight. The weight does not determine the color and shape neither. So based on your understanding of the real world, human experience, you do not understand. Now you need to use this so-called mathematical relationship to determine there. In this case, we derive from the limited set of the sample or a population we have that there's following relationship. Object color, weight. Determine weight. Why object color determine weight? If you look at the color, red 5, blue 5, yellow 7. So you can try this by trial and error. So if you're saying that if I know blue, do I know what color of the object? But what is the weight of the object? You look at blue, oh, it's 5, right? But if you ask the question reversely, if I know something weight 5 pounds, I don't know the unit here, but I say 5 pounds. If something weighs 5 pounds, what color do I know it is from this particular table? You don't know. It could be blue, it could be red, because you know 5, it matched to 2. So this leads to one important concept mathematically in set theory is that the left hand side together will determine or uniquely identify a value for the right hand side. If the value you identify on the right hand side is unique, then the left hand side is a determinant. So in this case, object color is a determinant. But again, if you lost somewhere in here, you say, how do I know? If I know the object color is blue, why is 5? Yes, this table says 5, but I can easily find some other thing that's not weight 5. But this is just an example telling you that the trick of math. It depends on the universe you're looking at, right? So in this case, we're only looking at the universe of this table only, not looking at the universe of the real human being world. This is the slide will confuse a lot of people, but hopefully that I make this my point clear now. And this relationship, color determine weight and shape, or weight and shape together, only happen in this table. It does not happen in other table or your true experience. And this type of example become, or this type of concept become very important when you are dealing with abstract stuff, right? When you keep track of keeping track of the real world physical stuff is much easier. You keep track of the sale, you keep track of the product, you keep track of people. That's easy. But when you try to keep track of something more virtual, say for example, in finance we have something called a derivative, right? So something that's when one of the main reasons 2008 that financial market crashed due to the derivative. Derivative is a product, a financial product. The best way to explain the derivative is that try to imagine some people try to sell you insurance. When you buy insurance, there are so many different terms, and once they tell you all these different terms, you got confused, right? And why insurance, or when people sell insurance, you feel confused? Because it's too complicated. That data set there contains too many attributes or columns can use to describe a insurance. And so when you try to use those derivative, it becomes a special expertise, and this special expertise actually ties very importantly to our data theory, right? So of course in finance that you got to be very good at math in order to handle all these abstraction or the virtual concept that you try to handle, and without confuse you more, I just kind of stop here at this particular point in time. Just tell you that there it's limited to the data set or data you're handling. In the classroom, I usually take a bunch of M&M chocolate to share with you the example. So if you buy a bunch of M&M chocolate, and you know that the number of color is limited in the M&M world, but in real world we have more than the color the M&M can handle. But so that once you know a color, you know probably how many M&M beads you have. But once you know some number, you don't know the number of that color. So that's that confusing logic is coming from. Okay. So coming from the earlier example of functional dependency, you have this derived number. We have this sometimes, and this is the second set of the learning objective I have in this particular lecture. That is, you have to be very careful in knowing something what we call a composite determinant. Composite determinants are using two columns to determine a phone number. Say, for example, if we go to our class, right? We have a class of 21, I believe, in this particular semester. So 21 students. So if we look at our student table, there are 21 students. Then we say, let's find a student and find out his email address. And so if I said use first name, yeah, it's probably good enough because we don't have duplicated first name in our class. But what if I have a class of 50? It's very likely we have a duplicated first name, right? So that's possible that you may not want to use first name as your determinant, or using database terminology as primary key, right? However, if you combine your first name with last name, you say, okay, John Smith, John Doe, John something. You combine first name and last name together. Now you have a more complicated name. and this name has a higher probability to be unique. That makes sense, right? So when you combine two column or two field, it's better. And if you want to avoid further confusion, you can say, okay, why don't we use the person's first name, last name, plus his social security number? All these two together, most likely you will get one person, not two, right? So that will probably be a good idea. So this is, but how many of this column we need to use? And we try, in design your database or create a database, you don't want to use too many columns, because too many columns become a management issue. We'll discuss probably somewhere along the line when we talk about the multiple composite key and create problem. Now this composite key is valid, and it becomes an important tool for us to identify the BCDF anomaly. But in this particular situation, what we need to know is, we sometimes need more than one column to generate a unique combination. You cannot have one column unique. You have two columns generate unique combination to generate a potential candidate key, and that will be used. And and the ultimate purpose to identify the key, there are two of them. One is, once you identify key, you can select one, use that as your primary key. The other one is, we can use key to do normalization calculation and to make sure you have a better design. And in functional dependency, the logical rule apply, and some example of a functional dependency can be explained here. And here there's no explanation about or terminology I want to explain. So I'll kind of go relatively faster in the next few slides until we reach some important concept, and we will wrap it up when we reach that important concept and explain it. So so this example telling you, okay, there one column SKU, very similar to your student ID. A lot of time that we see this something called ID or number. That's usually, and that number is actually some concept we call, another terminology called surrogate key. So surrogate key is usually a good key used as an identifier, used as a primary key in your table, and a primary key usually can determine the rest of the column of your table. In this case, you have SKU. SKU, by the way, stands for stock keeping unit. We talked about that last time from the inventory control terminology. And we have SKU description, and the description for each one of these numbers is slightly different. So even description can differentiate or identify other column as well. But buyer is a special one. And so this one just give you an example how to identify column and their dependency from one another. But still, again, it can be confusing. I'll leave that to you for practice. But knowing this is good enough to start learning normalization theory. And functional dependency can be easily derived as so the quantity, price, extended price can be determined by this your order. Each individual order is and so there's sometimes more like a transitive relationship. Order, stock keeping unit determine quantity price, and the quantity price determine extended price. So that can be seen in this relationship. So basically what we're doing is we look at the table and try to see are there relationship among these tables, and understand the relationship, you'll get a better sense of data. Right. So a lot of these profession, that when you become a inner circle, that's when you have this human intuition about the way they look at the world. So when you are writing computer program long enough, people write a simple piece of code, you can relate to that. When you handle data enough, the first thing you do now will be looking at, well, there any relationship between column. And if you have the habit, congratulations, you are into the database world a lot. Okay, so the goal is to make sure that the value is unique, and so we can identify determinant. The terminology called key is designed to describe that particular concept. So and this particular statement is important. I'll try to highlight this a little bit. So it's combination of one or more. So this word is important in terms of for you to know the essence of a key. So a key can be one or more. So it's never need to be a single column. It can be one or more. Right? So once you get the concept, and later when you see multiple concept, and you may not lost in the trick that I put into your quiz question. Right? So a primary key can have two columns. So if I ask you something about the primary key, let's see if I can find an example. Right? I'll do something real quick by moving the slide a little bit faster. Okay. So in here, there are two table description here. One is called order item. The other is called SKU data. And I briefly described what was a primary key already in my lecture. And the primary key that is usually represented by the underlying representation of the notation here. So here, that you will see that trick question coming out will be something like this. I will ask you, what is the primary key of order item? Order item. What is the primary key of order item? The first response to that, based on our regular person's response, will be order number. That is the wrong answer. The primary key for order item table is the combination of SKU and order number. Right? They use two columns to represent. So key, in this case, key is a combination of two columns in order item table. So that's one of the important concepts I want to explain here. So the second objective I have today, other than introduce the basic assumption function of relational theory, is to understand the terminology and concept of key. So let's do a little bit survey of the key, and we'll stop our lecture here. So these are the terminology we'll encounter in the relational database world in terms of the key. So you have a key. A composite key means that the key is composed of more than one column. And a candidate key is a key that can be used to determine all other columns, very much like our primary key. It is called a candidate key because there may be more than one column has that ability to determine the rest of the column. So one of our next job in normalization is, other than define relation, we're going to be defining primary key. Right? So once you identify the identifier called the primary key, you pretty much go into the second normal form. So primary key is a key that you use to identify the rest of the column, and candidate key can be many of those, but you select one to be primary key. And a surrogate key will be an artificial primary key that we as a database designer or manager created for the purpose of managing database. And most likely, a lot of these numbers are primary surrogate key. Say, for example, student ID, social security number. These are artificial number people created, or simply sequence number. You go into the any registration office, they give you a ticket, ask you to wait. Those are sequential. Each one identify one person, very unique. So that's called a surrogate key. Surrogate key because it's surrogate. It's just given by a third party, so we call them surrogate key. In the past, surrogate key is really a bad practice because every time you create a surrogate key, you waste the memory space by introducing a new data set, which is useless other than identify the row. But nowadays, again, memory space is no longer an issue. Surrogate key become a recommended key to be used in database design. Next one is called a foreign key. Foreign key is a key or is a column you use to insert to another column, another table, to create a relationship. And so when you find the relationship, the key from one table to another, is called a foreign key. So this is an example of the foreign key. So if you put a department name into employee, so in this two table design, we have one table keep track of department. The other table keep track of employee. And when we put department name into employee table, we can know which department the employee work for. And this department name, this little sort of insertion of key linking these two tables together, and that particular act create a whole magical world called a relational database, because they have relation, so we call them relational database. And that's it. And I think what I will do is I'll stop here by introducing two important concepts in our lecture today. One is that some of the basic understanding about functional dependency. The other is the set of concept called key that you have to understand. In particular, the concept of key is not one column, right? Key is a one or a combination of. A lot of time people will be very specific using composite key, but not all the time. So be very aware of what terminology you are using, right? So enough saying that. I will not emphasize more. I will use some exam and testing question to reinforce your understanding on that part. And well, that's it. And I'll stop the recording of this part here.